In exercise 3B, we're going to move on and use some of the terms that were defined in exercise 3A, and the way that they are used comes into calculus. So the calculus operations you've learnt, so that's the good thing. You will be differentiating and you will be integrating, but the process, there's no new processes for differentiating or integrating. What you will find is that there will be a big emphasis on the particular type of function that you're given. So in the beginning, to start the concept, we always have a function which describes displacement for us. So it's going to describe displacement. So the displacement, which we know the scientists use the symbol x, takes the place of a y or the function. So if I was using this notation, f of, actually I don't want to say f of x, if I was using the notation y is equal to something, what I'm going to have now is x. Because what does that mean? That is an expression or function here is going to be about displacement. So we introduced to that idea back in 3A. And also the function written here is not going to have x variables. It's going to have t variables. So y is like a little function in t, or displacement. Now we need to be reading x's as displacement. I'll make it something really simple, t squared plus 3t plus 2. So I've got a function about the displacement of, we can call it a particle, in terms of time. But again, back in 3A, those concepts were introduced. So we know that our horizontal axis is our time axis. Our vertical axis, and we could have positive displacement, negative displacement, but it is definitely our displacement axis. And that's going to be the focus for this exercise. You'll see as we get into the extension work, even these concepts here change. But if we're aware of what is on the axis here, it'll make it easier then later when we change them. So the only reason that much of this calculus was developed by the mathematicians is the scientists needed to be able to calculate. For example, in this case, they wanted to be able to calculate the instantaneous speed or velocity. They didn't necessarily have this change in displacement. It wasn't like at two different places and you could work out the change in the displacement over the change in time. They wanted it at a particular instant. Now, that led to the development of calculus, because we know that, well, in this case, we know this is going to be a nice parabola. Actually, I think that would cut way back there, cutting it to, that's as much as the parabola we'd see. It's actually going to cut the axis back there in negative time. And the other thing we know is we don't talk about negative time. We know that if we wanted, or if we got the gradient here of this curve, we're getting the rate of change of the displacement with respect to time. We know how to do that. It's called finding the first derivative. Finding the first derivative is the actual gradient, the rate at which this is changing, displacement, with respect to time. So that becomes our number one formula, or part of our formula, that we want dx dt. Understanding that is the rate of change of displacement with respect to time. So we would need to have originally had an expression for the displacement and in terms of the t variable, and we would differentiate it. So what we haven't identified is, what does that actually give us? Well, according to the scientists, the rate at which the displacement changes at a particular time, they chose to call the velocity. The mathematicians didn't care what it was called. They called it the first derivative. They called it the rate of change. But the scientists said, no, we want a name for it, and we're going to call it velocity. So that's where that name comes from. So this becomes our entire formula, that velocity is dx dt. Or, you can probably understand we had different notations for derivative back when we were learning about derivative, and a dot over the y was 1, or a little dash. You might see that occasionally. A dot over the x means the first derivative of the x function. The x function meaning a function about displacement in terms of time. Now, all we're going to be doing is using our understanding that velocity at a particular instant will be the first derivative of x with respect to time. And the calculus is really not difficult. Some understandings which are important in this unit is that displacement and velocity will have direction. So the displacement is a positive displacement or a negative. Velocity is in a positive direction or a negative direction. Distance and speed, the older or the more the initial terms you used for maybe these concepts, there was no direction given to those. Anyway, we spoke about that in 3A. Now, let's have a think about it. If this is, just have a look at this example down here. If this is the graph of where the particle is placed with respect to time, so it doesn't mean that the particle's going up and down. It means that from a fixed point, the particle was in the negative of the fixed point, and it came towards the origin or the fixed point. Then it went in the positive direction. Now, I'm really going to focus on what's going on here with the particle. It's going away in the positive direction until it reaches a point, and hopefully you can see right here at this particular point, and we'll be really interested in the point in time, something happens to the particle. You can probably see, because we can see that the particle now is heading back towards the fixed point or the origin. So if I go back to my just straight out horizontal, if this is my displacement and negative displacement, so the particle was down here somewhere. And what do we know? The particle came up, it got to the origin, it went on the positive side of the origin, and where I'm asking you to focus is at this point here. Now, what is the particle doing? There's a few things it's doing. We know it's going to head back. What does it have to do before it can actually head back? One is it must stop. It's another word for stop. If you stop, you are stationary. And that, it is no coincidence that these we've been calling stationary points. Because, like I said, much of this maths was developed before the scientists who wanted to be able to identify stopping positions, stationary positions. And so the mathematicians said, well, we'll call it a stationary position. And it's what was introduced, and we accepted that. But that's a good, just, I suppose, bit of background to help you understand maybe why it was called stationary. The other thing is, stationary point's not the only name we've given that. We called it a turning point. Well, let's have a think about it. Back here, when the particle was in a negatively displaced, came to the origin, went up, yes, it stopped and it turned. It turned and went back. Another reason why we would also call it a turning point. So just a little bit of background to reinforce those names you already know. What do we know about? So this is the displacement graph. We know that the particle will be stationary at these points where the gradient is 0. So this will be a really familiar and common situation you will investigate. You will want to know where dx dt is 0, where the particle is stationary, where the particle stopped, where the particle turned, etc. You'll get first an expression, then you'll solve it equal to 0. What name have we previously used to describe points? We've not only called them stationary, we've called them turning points, which makes sense when we start talking about particles and moving. Oops, sorry. And in some situations, see how it's saying here, how can they be described, these special points, how can they be described in terms of the displacement of the particle? Well, at times you could say that was the maximum displacement of the particle. Because if the displacement did have this sort of pattern, and we probably recognise that a bit like some sort of trig function, then it's never getting any higher than that. We can see that that's been called a maximum displacement from the origin. And again, that's been a name that we have used to describe this stationary point, turning point, maximum point. So if we were to be asked now to identify the maximum or the minimum displacement, maximum or minimum displacement, we know it's going to happen when the particle has moved as far from the origin, or at some point the particle stops, so that's equal to 0. We want the velocity equal to 0. What is the velocity? The velocity is dx dt. Now, once we've solved that, we will have a value for t. That will be an expression in t, and we will solve it equal to 0, so we will know at what time. But if we're asked for the actual displacement, where's our function about displacement? Our function about displacement was right back here, there. Our displacement about the our function about displacement will have been given. It's right back there. We will sub into that to actually find the actual maximum or minimum displacement. Now, mathematically, we've looked at differentiating a second time, the second derivative. So now, and we're going to do that now. However, what you will see drawn, if you've got a graph, is still time on your horizontal axis, but what you would be, what your function would be the velocity function, or x dot, and then differentiating that. So if we've graphed, or if we've got velocity in terms of time, now velocity we got from differentiating displacement, if we've got velocity, then we could be finding its turning points. We could differentiate, we could find dv dt, and find some things about velocity. So the scientists had a name for the rate at which velocity changes with respect to time. The rate at which velocity changes with respect to time, the scientists chose to call acceleration. So the second derivative of displacement, or the first derivative of velocity, is called acceleration. So acceleration is dv dt, or it's the second derivative of displacement, or it could be written as x with 2 dots. The process for differentiating you have learnt. There's nothing new in the differentiation processes.